So thank you. Thank you to the organizers for inviting me. Thank you to all of you for coming. I realize that I don't know most of you, which probably also means most of you don't know me, which also means I don't really know what your background is. So Daniele's goal was to alienate both mathematicians and physicists, and he has failed. My goal is to bore you completely out of your minds, and I might succeed. Okay? So in particular, I'm not planning to talk about anything new whatsoever. So I think the most recent thing I plan to talk about is about 40 years old. For physicists, it's very scary. This is boring old stuff. I'm trying to convince you it's not so boring. We have Q&A sessions, we have problem sessions. There is more stuff to be said, but that's not part of the plan for these talks, right? So many of you, from what I understand, do scattering amplitudes and modular forms and all that. So I want to do this in a very rudimentary way, but somehow my main message is to try to use algebraic geometric language, and then some things become trivial and some don't. And hopefully we'll see how this works. Please ask questions, then I might have a chance to know if I'm going too fast. Please snore very loudly if you're very bored, so that I know I should speed up. We'll see how that goes. So the plan, which does not quite align with 3 lectures, but anyway, it's the following. So we'll start by, genus 1, elliptic curves, the usual SL2Z modular forms. And with apologies to the audience here, I'm, for the purposes of this talk, a complex algebraic geometer. So everything everywhere is going to be over complex numbers. Everything will always be holomorphic. I will not touch upon anything that is not that. That's what we'll do. And I know that you know what this is, but I'll try to present different viewpoints on this, and we'll study this to death now. And hopefully then I'll say, and by the way, we can just generalize it in different ways quickly. Quickly is not going to work, but there are 2 different ways to generalize this. One is to higher genus Riemann surfaces, algebraic curves. And one is to higher dimensional abelian varieties. And I will try to present to you both of these generalizations, starting actually with this one. And then somehow what you get here is, a Jacobian of a curve, Jacobian of a Riemann surface. I'll use a curve and the Riemann surface completely interchangeably to get you more used to thinking this way. So a curve for me is always a complex, compact, algebraic curve of finite genus, also known as the Riemann surface of genus G. And the Jacobian of a curve is an abelian variety. And then somehow my goal is to prove, of course I won't really prove, but I will give you a proof as phase trisecant identities. Much of the work will be to explain what this is and why you might care. Actually proving this will not be the main time constraint. Okay, so that's roughly the plan. How far we get, we'll find out, hopefully to here. If we continue beyond, there is, the next 7 lectures are beyond here. Okay, fair enough? So that's the plan. Again, please help me speed up or slow down. I do appreciate it. If you cannot read what I wrote, ask. We have time for questions, and that's what happens. Okay, so the main protagonist of our story will be the theta function. So let me start by writing H. This is the upper half space, so this is the imaginary part of tau is greater than 0, where tau, usually people write it different order, but anyway. Tau is a complex number with imaginary part greater than 0. And then Z for me will be just a complex number. And the main thing that we'll focus on for a while will be the theta function. Excuse me, theta of tau Z. I'll just write it as a sum over the integers n, exponential, and I know that many of you know, but please bear with me as I write it in a weird way. Okay, That's the theta function. That's just the definition. I just wrote an explicit expression for a function of two variables, tau and z. Whether you call it tau or tau, I don't care. It depends on which side of the Atlantic you are at. But z is still z. And this is a sum. It's an infinite sum. It's sort of a Fourier series like sum. I promise that this is going to converge because n is positive and tau has positive imaginary part. So this is like I times something. So I times I is -1. So this is a negative quadratic, basically. So this will converge. Okay? I'm not doing computations. We're not going to discuss how fast this converges. Okay? What is this? So theta, of course, is a holomorphic function. So I'll be using as much algebraic notation as I can. So this is a holomorphic function like that, right? It goes from the upper half space, upper half plane, times c to c. And for the purposes of, for now, I will fix the tau. That is theta of tau z, tau fixed. And perhaps the main property in this point of view of the theta function is the following. I'll start looking at my notes so that I remember in which words I have to say it. Is that if I take theta of tau z plus a tau plus b, and here a and b are integers, then this is going to be basically the same as the original theta function, but there will be some exponential here. Okay? And we do have a problem session at the end of the week, so this means you should have problems. So problems will go in green boxes, and this is the exercise is to compute this. In particular, I'd like to observe that there is no b. b does not enter, which means that if I just translate by b, nothing happened. Okay? This function is periodic with respect to shifts by 1. It is not periodic by a shift by tau. Okay? So there is a notion of a theta divisor. So I would like to consider the locus z, complex numbers, such that theta of tau z is 0. Still for tau fixed, right? This is, of course, a locus in C, but it is invariant under this kind of operation, plus a tau plus b. Under adding anything like that, right? Because if this is 0, then this is 0, it's just a product. On the other hand, that's an exponential of some stuff that you're supposed to compute. So it's, in particular, it's a manifestly non-zero gadget, right? So if this is 0, this is also 0. Okay? So this is to say that this 0 locus of the theta function, which is properly called the theta divisor, is well defined on the quotient. So notation or definition, maybe. E sub tau, this is an elliptic curve. Just a fancy way to say genus 1 Riemann surface. This is by definition just the quotient of C by Z plus Z tau, right? So if I were to draw this for you, I will draw the usual picture that all of you have seen. This is 1 tau, 1 plus tau. And then I identify the opposite side. So this gets identified to this gets identified to that, right? That's a picture of an elliptic curve. That's a picture of a genus 1 Riemann surface. And the point is that this locus here, let's call this locus capital theta. This is a capital theta, if you can read my handwriting, right? Okay. So theta side C descends is a word I'll explain in a second, to a theta tau inside an elliptic curve. Okay? So all I'm saying is that this locus theta is invariant at the translations by this lattice, so that it has a zero locus which is well defined on the quotient. Okay? This is all an extremely elaborate way to say something completely trivial, because what this thing is just 1 point, 1 plus tau over 2. Okay, that's an exercise. Okay? So I claim that, in fact, in this parallelogram, in the fundamental domain for the action of the lattice, there is a unique point where the theta function vanishes, and it's right here, smack in the center. How do you prove this? That's your exercise, but let me tell you how you should do it. So first of all, you should convince yourself that that point, 1 plus tau over 2, is a zero of the theta function. Convince yourself of that, you observe some parity, and that's easy. Okay, so you will have found 1, 0. It's a little too early to celebrate victory because you need to know that there are no other zeros, okay? But you probably know how to compute the number of zeros of a holomorphic function within a domain, right? You compute the integral of d log z, basically. I mean, i's and pi all equal 1, right? So you compute the integral of d log z along here, but you know the transformation property of the theta function, right? You know that it is invariant on the translation by 1, so these two integrals will just cancel. And you know how it transforms if you shift from here to here. So you'll be able to compute that integral, and you'll be able to convince yourself that there is only 1, 0. That's the 0. Okay? Raise your hand if so far everything has been completely trivial. Okay, so I think you have found a couple people who are designated as teaching assistants for the class. Please. I do not differ by a factor of 2. So this is a standard theta function. This is the definition of the standard theta function, and I will insist on this. Okay? Because there will be non-standard theta functions shortly, and the factor of 2 will show up. That is Riemann's theta function as written, not really by Riemann first, but anyway, yeah. That's a theta function. Okay? Quite sure. Okay? Okay, so far so good. So this was a nice exercise. So what did we learn? We learned that we have this function theta, which has a unique zero on the elliptic curve, which I'm thinking of this way, at this point. Here is a question you can ask. What do all, leave some space, functions on the elliptic curve look like? Okay, so that's very ambitious because I need to say what kind of functions I'm interested in, right? You can ask about holomorphic functions. You remember, I'm in the holomorphic world, I'm a complex geometer, I know nothing about real numbers. Okay? So what do all holomorphic functions on the elliptic curve look like? Well, they don't look like much, they're constants. An elliptic curve is a holomorphic compact space, so there is a maximum principle. So any function must achieve its maximum. In an interior point, there are no non-interior points, so there are no holomorphic functions. So all holomorphic functions on a compact Riemann surface are constants. Very boring. I know what they look like, but there is no interesting question. So a more interesting question is meromorphic. Okay? So what does a meromorphic function look like? So I will write f is a meromorphic function. I'm an algebraic geometer now, so I will think of this as a map to P1. For me, P1 is CP1. I will probably stop writing C very quickly, okay? That's what a meromorphic function is. It's the same as a holomorphic map of two Riemann surfaces, elliptic curve to CP1, okay? What is this zero? And let's say Z1 through Zn are zeros of f counted with multiplicity. Let's say P1, Pn are poles of f. Okay? And let's say M1 through Mn are their multiplicities. and let's say k1 through kn are the multiplicities of pi as poles, right? So you can have a first order zero, second order zero, and so on. Okay. So suppose I want to have a function which does that. How could I possibly construct explicitly such a function? So I want a function on an elliptic curve, which is meromorphic, which has such properties. Well, to start with, how do I construct a function that has a zero at a point z1? Well, nothing could be simpler. I just take theta, z minus z1, plus 1 plus tau over 2. Okay? On the elliptic curve, this vanishes precisely when the argument is 1 plus tau over 2, right? So this is 0 if and only if z is equal to z1 as points on the elliptic curve. There is a problem. This is not really a function. It's not periodic. It's not a function on elliptic curve. Never mind. Okay, so you can actually construct function f. So what you do is you take a product for I goes from 1 to n of this kind of thing. Sorry, this should not be the same index. Sorry, the number of poles, not since multiplicities are different, is not equal to the sum to the number of zeros. Okay. You could allow multiplicity 0, but that's not very exciting. All points are multiplicity 0. Yeah. Let's just look at on a 0 poles. Okay. Now this should be mi. Product I goes from 1 to s, theta to the ki, d minus p, I. There is up to a constant factor. So I claim that if I want to have a function, a meromorphic function elliptic curve, with prescribed zeros, prescribed multiplicities, prescribed poles, prescribed multiplicities, I can just write it. That's a formula. Okay? You can check that it has the correct zeros, right? It vanishes when z is equal to zi because this guy vanishes with multiplicity mi. It has a pole with z equal to pi with multiplicity ki because this guy vanishes, okay? So, exercise, prove this, and deduce Abel's theorem. I don't know whether you can see that this is green as opposed to white. Yes? Borderline, okay. So I won't tell you what Abel's theorem is because this will take us too far apart. But basically the point is I want this to be a function and not a section of some line bundle. And the general statement is all sections of all line bundles can also be written this way. Okay? And this is what I want to discuss now. Okay, raise your hand if everything was still completely trivial. Good. Raise your hand if you're lost. Maybe I should turn around and ask this question. Raise your hand if you're lost. Okay. Will somebody tell me if somebody was lost? Okay, so this is the analytic theory, if you wish, of meromorphic functions on one elliptic curve. Now what I want to do is I want to talk about line bundles and sections of line bundles. And I think this is not necessarily part of the language that you fluently speak for all of you. Okay? I may be wrong. For some of you, this will be exceptionally boring, so just you can get a coffee in the next 10 minutes. But I'll try to do a discussion of holomorphic sections of holomorphic line bundles on manifolds. Okay? So this is,
preliminary question?
Please.
Will there be anything new, or are you writing the same thing?
I will do this in much more generality, because I want this in much more generality. Okay? So I'll write this in general. We'll return to this in a day. I want to phrase this in a different language because this language will be useful. Okay? So interlude, holomorphic line bundles on complex manifolds. Complex. Okay, so X is a complex manifold. So this means it's a union of some charts UI, right? So the charts are UI. So UI is just a disk ball, open ball. N. I'm suppressing the notation for how it's identified. And there are gluing maps. UI intersect UJ, right? So this means that this has coordinates Z1, Zn, and here I want to write that Z1i, Zni, Gij, I. Okay. So this is just a notion of a manifold. These are holomorphic. I have a chart, so I have one ball, another ball. This has coordinates called Zi, this has coordinates Zj, and I have to say how I can go from coordinate Zi to coordinate Zj on the overlap. A complex or holomorphic line bundle L on such a gadget X is the following. It takes a union over all I of each UI times C, and you glue, okay, or using some function Fij, which is going to be a function from UI uj to C star. This is holomorphic. So what you're going to do is, this guy has coordinates Zi1 through Zin. This has coordinate, maybe let's call it xi, right? And I want to glue by this map, basically. So I want to say Zi1, Zin, xi is equal to, well, this gluing. Okay, so what really happened? So I had two coordinate charts, one coordinate chart and another coordinate chart. And I glued them on the overlap. That's a bad picture, right? So let's draw this picture. So UI, uj, and over each of this, I have uj times c, and here I have ui times c. Obviously, my drawing skills fail because there are too many dimensions, right? And this thing here has a preimage here and a preimage here, which I want to identify. So of course, I know how to glue the coordinates on the base, but then for each line, which is a fiber over this point, for each line, I want to glue that line to that line, not in an arbitrary way, but in a linear way, right? So as a result, this total space, this union, will map to X, which is the union of and here, each fiber. Okay. So a line bundle is just something which has a map here. Each fiber is C, but I want to say that somehow the standard way to say this in words is to say that for each point in X, there is a small neighborhood. So this preimage here is a product of this small neighborhood and C. Okay, that's what you say. I wrote this explicitly in coordinates because if you're trying to do this here, you'll want to do coordinate charts. Okay? So all I'm saying, again, is that a line bundle is just something that over each point of x, you have a C fiber. But this C fiber, when you need to give a coordinate on this, and you can only do this locally. And if you go around, the coordinate will change. And this is what tells you how the coordinate is going to change. Okay? A section S of L, what you write is S is a section of L on X. Holomorphic section is the following. So let's call this map pi. So the pi is the map from the total space of the line bundle to X. It's just a map S, X to L, such that the algebraic way to write it is to say that pi composed with S is the identity map on X. What this means is here is my X, here is my L, right? And this maps here. And then at each point here, I have a fiber. And I just need to choose a point in this fiber. At this point, I have a fiber, which is a complex line again, so I choose a point. So a section is this. Okay? That's a formal way to do that. Okay? Let me try to do dry erasing for now. I might regret this later on. Questions? Is this still okay? So again, a complex holomorphic line bundle is just something where you have, complex lines as fibers, and they identify, this does not work, and they are identified over charts. So locally, around every point of X, a complex line bundle is just a product of X and a complex line, but globally there is some non-trivial structure. The simplest example of a holomorphic line bundle is just a product of X and the line. Then I can choose one chart UI, or rather I can choose many charts if I need to glue X, but the transition functions here will all be identity. There will be one. Okay. A meromorphic section L is a collection of meromorphic functions I that glue correctly. So a meromorphic section is just, in each local chart, I just take a meromorphic function, and this means I have allowed poles. And then they would still agree. Glue correctly means that if I take Si valued at the point Zi, and I take Sj valued at the point Zj, this is still equal to Fij of Zj for any point overlap. Okay? I can no longer say that this looks like that because a line bundle does not have infinity. But mentally, if you somehow added infinity, you would allow yourself to hit infinity. Okay? definition. For any meromorphic section S of a line bundle, holomorphic line bundle, L on X, its divisor is the divisor of S is a formal sum where EI and the components, the irreducible components, locus 0, this is I multiplicity of vanishing and infinity also be in the multiplicity. In the order, I guess you're easily right. Okay, this was fancy language. So what does this really mean? So this means for the case we care about now, we're going back. So if you didn't like that, don't worry. For X being a Riemann surface, and L on X being a line bundle, if S is a meromorphic section L, and divisor of S sum di pi is a formal sum, just a notation at the moment. Pi, where this is the zeros, multiplicity, these are poles. Okay. So this is just a convenient way to keep track of all the zeros and poles of a function, or more generally of a section of a line. It depends. It depends on whether, when I write the order of the pole, is the second order pole comes with. So the second order pole here should come with multiplicity -2. We can discuss whether we call this the order or minus the order. Okay. Yeah, that's the definition. But in some sense, I shouldn't really be distinguishing them. So in principle, this is just all, I take the sum over all points with the order at that point. At most points, the order is 0. The function is just not 0, not infinity. So most points will drop out. So I should really write the sum over p being an x of the order at the point p of s times t, right? And this is, in fact, even though I'm taking the sum over all infinitely minor points on X, this is really a finite sum. Okay? So that's, now this tells you how I think about the orders. Okay, I know this is maybe pure suffering, but there is a purpose to that, because it allows you to say things nicely, which we will do shortly. I'll be done in 2 minutes. So if you're suffering, feel free to just tune out for 2 minutes and we'll be back to friendly elliptic curves. Normally, if you're teaching a course on complex manifolds, I think this discussion takes a couple of weeks, which we don't have. So please don't consider that everything I said is completely correct either, but I think so far I haven't lied. So we're almost done. There is one remark. If S1 and S2 are meromorphic sections of the same line bundle L on X, then what happens if I take the ratio S1 over S2? So locally, this is a meromorphic function. Locally, this is another meromorphic function. The ratio is also a meromorphic function. How is that going to change at the change of coordinates? Well, S1 is a section, so it's going to multiply by F. S2 is also a section, it's also going to multiply by the same F, so they're going to scale the same way. So then this means S1 over S2 is a meromorphic function on X. Okay. More generally, if S1, I'll start writing meromorphic sections. I feel horrible about doing this, but I will. X, L1, S2 is a meromorphic section L2. Then, if I take that product, S1 times S2, it's also a meromorphic local thing. So it's a section, a bundle called L1 tensor L2. So line bundle with Fij L1 tensor L2 is equal to Fij L1 times Fij. Right? So this F's, these gluing maps are what define a line bundle. But these are just complex numbers. I can multiply them or divide them and take powers to do whatever I want. So this means I can just define a line bundle, which is a tensor product of line bundles, by taking the product of this function. Why did I write more generally here and not also? Because if you take 1 over S2, that's certainly a section of a bundle where I've taken the inverse of Fi's, right? So if Fij for L1 is equal to the inverse of this is 1, so this is in a section of a trivial bundle, there is no transition. Okay? Have we suffered enough? Almost enough.
Is this the end of the interview?
Yes, almost. We'll have one more remark. Okay? So this remark comes under the guise of exercise to understand all this. Okay? Basic example of a line bundle is the so-called line bundle O of 1 on Pn. Okay? On Cpn. So you know that Cpn is just you take vector space, you take out the 0, and you take a quotient by C star. Okay? And what is O of 1? I'll tell you by telling what the functions are. So sections, space of sections on Cpn O of 1 are homogeneous linear polynomials in y0 to the n. These are coordinates to the n. Okay? So I've defined a line bundle by telling you what its sections are. This really means I should find an atlas of charts for CPN, which are coordinate charts, and I should compute how the linear polynomials transform. This will tell me the line bundle. So if you want to make sure that you understand all of this, and I highly encourage you to do this if you haven't worked with line bundle before, make sure that you understand what this line bundle does, and then try to understand what are the sections of its nth tensor power and how many there are. Okay? Okay, so the interlude is officially declared over. This piece of paper is gone. Why did we suffer through all that? Because now I want to tell you something. Now I want to tell you something about elliptic curves. For that, I would have needed half of the interlude, but eventually I want more generality. But questions on this, please do ask. Now we'll use a small part of this.
Yes.
Yes. Yes.
Why not stop this?
There is some technical issue here. So there is a very well-defined notion of a P1 fibration. I can just have something which fibers with P1. But then I need to mark in this P1 the infinity section. P1 doesn't, I mean, it's a sphere. I can declare that point to be infinity, but I better declare it everywhere at once. It has to, so basically, I can, given a line bundle, I can try to add a point at infinity. I'll get a P1 bundle, but with a marked section at infinity, which is extra data, which is less natural. And there are many things you can do with line bundles, which would be not true if I just take a P1 bundle without an infinity section. This is the natural setup. More natural setup is vector bundles of higher rank. Then you would not get away from this by just taking 1 point. More questions? Okay, so I think this qualifies as undue pain and suffering. Let's go back to elliptic curves. I promise there is a reason why we did this, not just to say something. I want to be able to deduce things very, very quickly and very cheaply from this language and this machinery. And one thing I would like to mention here is the following, that if you have a compact complex manifold and you have a line bundle in it, and you look at the holomorphic sections, the holomorphic sections are a finite dimensional space, just because everything is algebraic, everything is finite, everything is compact, so you only have finitely many sections. And that's very useful. Okay? So if you just ask about all holomorphic functions on C, that's a horribly big space, right? If you ask about functions on C which are meromorphic, including at infinity, and have a polar force up to 5, that's suddenly a finite dimensional space. If I now have a line bundle, this line bundle Pn, that's a finite dimensional space. So all complex line bundles on compact complex manifolds will have finitely many sections. And I'll get an unbelievable amount of mileage from that now. Okay? So let's get back to an elliptic curve, if I may. So you remember I have an elliptic curve, which is a quotient of C by Z plus Z tau. Yeah, and by the way, if you didn't like the interlude at all, you should still be roughly okay now. You'd have to believe me on a few things. That's an elliptic curve. You probably also know another way to think about elliptic curves, right? Yes, okay. So somebody does. So they are algebraic curves. You write them as polynomial equations. So you want to write it also as something like y squared is equal to x cubed plus g2x plus g3 or something like that, right? How do I get from here to there? If you ask Ollie, you write the Weierstrass P function. Yes, I know, Weierstrass knew that also. That's not how I want to get there, right? So that's an explicit function. How do you in principle do that? So I have some object, which is a complex manifold, And this is a locus. This thing here, I should really think of as a locus in CP2, right? Or CP1 cross CP1, let's not worry about that too much. How do I go from here to here? Well, I better construct a map. So I want to construct a map, hopefully an embedding of this into a projective space. How to embed in general a variety X into some projective space, right? In my case, I want to embed an elliptic curve in P2. So you see, suppose L is a line bundle with many sections. I don't want to say what many is. Let's say S1 through Sn, S0 through Sn, this is the basis of the space of sections. This is a finite dimensional space that I just mumbled. So I have a finite dimensional, these are holomorphic sections, right? These are holomorphic. Now on, if I don't write anything, everything is holomorphic. So suppose I have that. But then, if you take a point X and X, and you just send it to the set of values of these sections, I have no idea what I just did, by the way, right? This section is a point on the C fiber. It's not a natural identified C fiber, so I don't know, it's some point. But the ratio of such points are well defined, because if I go to a different coordinate, the thing changes, right? So this thing here is a well-defined point in the projective space. Not all coordinates are 0. So this gives me a map from X to a projective space. Okay? So if I have a line bundle that has many sections, so if I had many meromorphic functions on a thing, right, I can just take their values and declare them to be coordinates. More generally, if I take a line bundle with many sections for some reason, I can do that. What do I really need to do? I need to have at least 2 sections, otherwise I don't get anything. If I have at least 2 sections, I also would like for them to not vanish simultaneously, all of them, because then I don't get a map. And I get a map. If I'm exceptionally lucky, I'll get an injective map, right? I'll get an embedding. I'll embed my X into a projective space. Okay, very good. So now, this is a general machinery, but somehow in a friendlier way, maybe. What can we do for an elliptic curve? So how about line bundles on elliptic curves? Well, you know, the function theta of z, tau fixed, as we discussed, has some transformation property. So it's not really a section. It's not really a meromorphic function in an elliptic curve, but it's a section of some line bundles denoted theta. Which is given by the automorphic property of the theta function. Okay? So this is what also I mumbled somewhere through our pain and suffering. So this is an elliptic curve, right? Which I'm thinking of as this, right? Identified. I can think of this as a manifold by just taking charts, you know, around here. And then the transitions are all trivial, except when I want to glue from here to here, it's still trivial because my theta function is trivial, is periodic under translation by 1. But if I want to glue from here to here, the theta function multiplies by the exponential that you were supposed to compute, right? So this means that this is the transition from a small chart here to a small chart here is by multiplication by the exponential thing, which is an element of C star, which depends holomorphically on everything. So that's a line bundle. This is a line bundle, okay? So I have a natural line bundle here. Theta function has a unique 0, which we decided, right? And in fact, it's the only, it's a fact which is really an exercise. This is to say, that this bundle has a unique section, which is the theta function. Basically, if you had another holomorphic section, you would divide them. Where would the thing have zeros and poles? It doesn't have much choice. There is Abel's theorem, so no choice. Okay. Okay. Well, that's actually bad news if you think about it, right? I wanted a bundle with many sections to have an embedded in projective space, and I have one section. I'm stuck. What can I do? Can I somehow construct a line bundle on an elliptic curve that has many sections? Well, the answer is yes, and the answer is on the blackboard, which I will erase in a second. But we can take tensor powers, right? We can take tensor products. So if the moment I have one line bundle, I get many more by considering the tensor product. So let me do that. So I have so the dimension of the space of sections of theta is 1, but what I can do is I can ask this theta bundle to the power n. What is this? Okay. So how do we construct sections? So in down-to-earth language, what does this mean? I want a function on the upper half, on C, a function of Z, which is translation invariant and translation by 1. And when I translate by tau, it multiplies by the exponential that theta multiplies by, but to the extra power n. Well, one easy way is to just take the theta function of Z. I'm suppressing tau, it's fixed. And just take the nth power. This certainly works, right? No problem. Okay, I've constructed one section, doesn't quite qualify as a grand success. Okay, but notice that for any point, let's call it epsilon, which is a n torsion point. So this is n torsion points. So this means this is just you take Z plus tau Z, you just divide by n, right? What I can do is I can take the theta function of Z plus epsilon and raise that to the power n. Why is that an interesting thing to do? Because this epsilon is somehow translation. So this is going to be a section on the elliptic curve on certainly the nth power of whatever bundle this guy is a section of. And this will be a translation by epsilon. This is translation. Now, on an elliptic curve, you can translate by an arbitrary point. So you write the automorphic factor for theta. You just replace Z by Z plus epsilon, right? So this thing here is equal to, and this is something you can check by hand, but this comes from some general theory on abelian varieties. This is the translation by n epsilon of this. So that's a zero translation by 0, right? This epsilon was an n torsion point, so n times that point lies in the lattice, right? And so it doesn't do anything. So this is So it's a section of the same bundle. So exercise, prove this directly by computing automorphy. Automorphy. Okay. So I get a section. So I take the theta function, I take its nth power, but I translate it by an n torsion point. And then I will still get a section of the same bundle. So I get, if you count n squared such sections on the n squared torsion point. Right, so let me try to draw an example. So for n equal to 3, what are these torsion points? Torsion points are just this. Right? These are all the 9 3 torsion points on one elliptic curve. I get n squared functions. Question: are these linearly independent? I've constructed n squared sections, but there is no reason that they should be different. They should be linearly independent. Maybe there are many relations among them. So let's compute this. So this is an exercise that somehow will use a bit more machinery of dividers and so on Riemann surfaces. This uses Riemann-Roch theorem in this basic example, but you should think about the more general higher genus version. With the following, the exercise says that H1, and I don't want to tell you what this is, an elliptic curve 0, which implies also that H1 nth power of this is also 0, which implies that node dimension of H node equal to the Euler characteristic of this bundle. Okay. And this thing, so I wrote a bunch of symbols, which may or may not make sense to you, but I'll tell you what the upshot is. The upshot is that this thing here is just the top self-intersection number of this, the first power. So this is the degree, the number of zeros of theta to the n, which is n. Okay? So this is a formal way to prove. There are other ways to do it. You can do this by automorphic factor analysis. This is more elaborate. So the dimension of the space of sections at the end of the day is n. Okay? This is a purely algebraic computation. I won't develop the full homology theory and intersection theory. This works for high dimensional abelian varieties, as you'll see tomorrow. I'll write the same formula with a bunch of g's added. This will be exactly the same. The upshot of this thing is that it's very easy to compute that this n's or the theta functions, there should be only n of them, while I have constructed n squared of them, which means that these guys are definitely not linearly independent. Okay? I've constructed n squared elements in an n-dimensional space. Yes, because if you have sections of different line bundles, if they were to satisfy a linear relation, I would look at the automorphy. They would just scale differently, so they cannot. So the scaling would have to decompose. So the linear relation would have to decompose under the action of automorphy into different eigenspaces. Okay. You don't need much time for lunch, do you? So we can go on for a while. No, and I know that I should end in 15 minutes according to the schedule. And I promise there'll be no more technical interludes of this nature, but we do need this. You see, I'm getting stuff out of the language. Questions while I'm erasing, or in general? Okay. So claim, and you can treat this as an exercise, but I'll explain that this is easy. For any epsilon, which is a point in Z mod n, right? I can take the thing called theta, capital theta. I'm sorry that this notation clashes with everything, but that's standard. Theta epsilon tau Z, which is going to be theta function of n tau n Z plus tau epsilon. There is some small exponential here that I don't want to write for you. Is a section okay. So I did something horrible. I did what I was asked before. Did I not forget a factor of 2 or n? So I just added this factor of n here. I added a factor of n here, and I did not add a factor of n here. Epsilon in this notation is an integer, right? So I mean, I view this as just 0 through n minus 1. So if I added an n here, this would, by automorphic property, disappear. It would just give me some exponential. But here I've taken the theta function here, and I translated it by something else. What does this correspond to geometrically? So here is my abelian variety tau, which is 1 and tau, right? I also have an abelian variety called E, say, 3 tau, E n tau, which looks like this. This is 1, this is n tau, tau plus 1, right? So this theta function looks like it lives here, right? Because I have my argument as n tau. There is a map between these guys, which is an obvious map. You just cut up in pieces and you put each piece here, right? So this fact here, together with what I'm going to write, is a manifestation of what is called the isogeny theorem. So isogeny means finite map. So finite means all pre-images are finite of abelian finite surjective map. Abelian varieties. And there is a general isogeny theorem that basically tells you how theta functions change under isogeny. I won't write this fully, but from now on, n will be 2, basically from now on, for the rest of these lectures. And I want to write one formula. So that's epsilon delta corresponds to a point tau epsilon plus delta over 2, which is a 2 torsion point Zebulon right. So this is one of these 4 points. Okay. So I am just specializing now the discussion we had before to the case n equal to 2 because it's more explicit. Then I can take the theta function, tau z, plus tau epsilon plus delta over 2 squared, right? This is what was on the blackboard before. These are these guys, right? It's just this thing written explicitly. This is a section of the two theta bundles. So it transforms on one elliptic curve as a square of the theta, as the usual theta function transforms. There are 4 of these guys, depending on what I choose. And I know that the basis is given by these guys. So I can take a sum of, I'll use sigma to distinguish letters in Z mod 2. So that's a silly way to write a sum. There are 2 entries in the sum. Please bear with me though. And I know that this, I must have an expression of this sort. Because as a function of Z, this is a section of this bundle. The basis for the space of sections is given by these 2 guys. So any element is a linear combination of these 2 guys. So all I need to do is tell you what the coefficients here are. And the coefficients here are explicit. They are equal to -1 to the power theta delta, theta, sigma plus epsilon, tau 0. Okay? Notice there is no Z dependence here, right? From the point of view of Z, this is a constant, right? This does not depend on Z. So what I said is that the square of the theta function is a linear combination of a chosen basis. There is a good reason to choose this basis, not some other basis. And that's how the linear combination works. Okay? Exercise. Prove this. For n and g. This will be something you will do tomorrow. Okay? This you can just prove. Okay? You can prove this in many different ways. You can try to prove it by comparing the Fourier series expansions. Doable, utterly not fun. Certainly doable, I've done it more than once maybe. Not fun. But let me say some more. Good. Roughly where I thought we would be. Okay, so what I want to do now is, this is basically the end of the story for genus 1, except I want to tell you that all of the suffering was not for nothing. I want to tell you that just by looking at what we have done already, you will be able to prove many, many things. Oh well. That people might care about and have cared about a lot. So this thing here, this is called Riemann's bilinear addition formula. This is a classical name for that. This is just a special case of the much more generalized ordinary theorem that I'm not stating for you. Let me get some corollaries. So that's a theorem. Corollary. You notice you can start playing various games here, right? I wrote some identity. I can then set Z to be what I want to be. I get stuff. And then I get many sections here. They satisfy linear relations. I get stuff, right? So for example, you can get one of the most classical identities. I don't want to go over this notation, but this is basically you shift by nothing. Tau 0 is equal to theta to the 4, 1, 0, tau 0, plus theta to the 4, 0. tau 0. I'll write this notation tomorrow, but basically this just means shift by nothing, shift by tau over 2, shift by 1/2. Okay? How do you prove this identity? You look at each of these things, expand, you get a triviality. Okay? This has a number. This thing has a name and number theory. Exercise. Prove this. Find its number theory meaning. This is an equation between Fourier series. If I just formally take the force power Fourier series, there'll be a way to represent some number as a sum of 4 squares with some shifts. So this tells you that the number of ways to represent an integer as a sum of 4 squares is equal to the number of ways to represent it as some other sum of 4 squares with some shifts, and some other ones counted with multiplicity. If I stated it that way, I don't remember how to do it, but even if I knew, and if I were to ask you to prove this, this would be incomparable amount of pain and suffering what we had to do, okay? There are many other identities. For example, there is an identity of this sort, so dz, theta 1, 1, tau z, valued at 0 equal to 0, z equal to 0, is minus pi times the product of Yes.
Your sigma delta are just what I know.
They are theta 1, theta 2, theta 3. I don't remember which one is theta 1, which theta 1 is theta 2, which one is there. And there is a reason I don't remember. Because my personal interest is higher genus. Right? And in higher genus, there are going to be 2 to the 2g of these things. Okay. And the natural labeling is by points in z mod 2. Right. Right. So this is the theta 1. Yeah. So this is a Jacobi's triple product identity. Right? This is the derivative of the odd one is equal to the product of the 3. So theta 1 prime at 0 is equal to theta 2 times theta 3 times theta 4. For saying this, I don't need to remember which one is theta 2, which one is theta 3. There is no inherent way why this is 2, 3, and 4. I know. 1 second. This does not immediately fall. From Riemann's bilinear addition. There is still a very easy way to prove it. And that's your exercise to find that. But it does not just follow from that theorem. Yes? The theta epsilon delta tau z is some exponential factor that I don't care about for these purposes. Times theta tau z plus tau epsilon plus delta over 2. Okay, this will be the first formula on the blackboard tomorrow. Okay, so I should finish by an annoying exercise. The purpose of this exercise is to be annoying. Exercise. Find in the literature an identity among theta functions with characteristics, this guys. Characteristics in genus 1. Just find one. There are hundreds, thousands of them, and prove it. As follows. Okay. So want f of z is identical equal to 0, right? That's what the identities look like. It's an identity. Something is 0. Then f of z is always going to be a section on your favorite elliptic curve of the bundle theta, because there are no other bundles. Maybe there is some translation by some point A if people haven't written their identity very nicely. So these are all the bundles there are. elliptic curves. Then the dimension of the space of sections is equal to n. F vanishes at n plus 1 points, counted with multiplicity. You have to mumble a little bit more, but this basically implies f of z is identical to 0. This is not really meant to be a joke. I know it sounds like a joke when I say just find any identity in the literature and prove it. You would be surprised by how often you will succeed. You need to say something here. So basically what I'm saying, I have an n-dimensional space, and I have an element in this n-dimensional space. And to ensure that this element is 0, I need to say that it satisfies, excuse me, n plus 1 linearly independent conditions. So this linear independence condition is something that I swept under the rug here. So you need to say that the conditions for the thing to vanish at different points are independent. This is the case as long as you make sure that no points are plus minus each other, because this is the only issue. But if you take an arbitrary collection of n plus 1 points on an elliptic curve, they will impose independent conditions on sections of theta. The argument works. Okay. I have written many referee reports by using this. Okay? Just beware. If you find an identity which is possible, which does not work this way, come and see me. Happily try to work with it. This is an extremely, what I want to say is this thing here is very innocuous looking, but it is a very powerful tool. If you try to prove identities like that by brute force, you'll be suffering for a long time. This is really just that, right? And the reason it happens to look so nicely is sort of luck. But the way you know it's true is you just rewrite it in terms of this, you get immediately triviality, right? Many other identities you will also get this way. They may be useful, they may be very interesting, they may be more symmetric, they may have fewer terms, more terms. There is no guarantee how this is going to work. But the proofs of almost everything will follow this strategy. You just have an n-dimensional, often 2, 3, or 4-dimensional space, because many identities don't go beyond degree 4 and theta, so they're usually sections of 2, 3, or 4 theta. So there are 2, 3, or 4 sections. You write something, you check that it vanishes at 4 points, you're done. Okay? This works in high generality. So do this as an exercise. If you encounter any identities you want to check, it will tell you very quickly whether it's true or not. You just evaluate a bunch of points. So that's it for today, because I'm already a couple minutes over time. The plan tomorrow is to do abelian varieties. So we'll do the same, except there'll be a G in 25 places on the blackboard. And this will be higher dimensional theta functions, Ziegel modular forms, and Ziegel-Jacobi modular forms. You should keep in mind the interlude we had today about line bundles. This will not really show up tomorrow, because there is a Q&A session. We can discuss it further for those who care. It will show up a lot in the third lecture when we'll talk about Riemann surfaces. If you're thinking about the future, try to think what you would need to do the same in higher genus. Okay? For higher dimensional abelian varieties. That's it. Thank you. You can clap, then you can ask a question.